Good day. This is the fourth in a series of videos designed to explain how to create predictive models which are simultaneously explicable and precise. Today will not be a lecture on some grand theory, although the previous two videos dealt with that. The reason why we needed those, though, was because now we are going to actually be applying the ideas that we developed in those previous videos, in particular with respect to missing variables and with respect to variable transformations. So both of those ideas will be applied in today's video. But today we will be simply looking at code which now implements those ideas, looking at the output and seeing what to do with it. Now, where are we going with this? Well, remember, if we want a model to be precise, what that means is we have to think in terms of conditional expectations, which means we have to think in terms of functions which are dense in the space of continuous functions on the hypercube. And for models to be explicable, the function set has to be sufficiently simple when you write down the function so that you can understand what exactly it is saying. Now, in our case, we have selected, or we will be creating, what are known as MARS models. That is to say, multivariate adaptive regression spline models. But before getting there, we have to address at least two topics. One has to do with the idea of minimum weight. And so you have categorical variables. They take different values, and they take these different values with different frequencies. But the question is, how much weight, how many observations do we need for a particular value before we start believing estimates which come from that? And so that is a question that we will answer later on, but one for whose preparation we need to begin now. Similarly, we need to then think about, well, do we want to group together values of categorical variables, and how are we going to do that? So again, we will be making steps toward that in this particular piece of code. Now, how do you think about categorical variables? Well, as we discussed last time, when you have a categorical variable which takes n values, so for instance, state in the United States takes 50 values, you don't have a single variable, you have 50 binary variables. And so what would a grouping of them look like? Well, what it would look like arithmetically is to simply take a partition of the set of variables, the set of binary variables, and sum their columns, sum them. And that would effectively be a grouping of the variable. Now, the question is, well, how do you do this? Because obviously there are 2 to the n subsets of any variable, categorical variable that takes n values. So how on earth do you root through 2 to the n different possibilities for this group or that group and this thing and that thing? Now, admittedly, there's fewer partitions, but it's still a very intractable problem if you want to do it brute force. And that's just one variable. But now you're going to have multiple variables. So gee whiz, how do you deal with that? And we will get there eventually, but like I said, the preparation for that begins now. But the reason why I mention it is just to keep that in mind, that that's what we're going to be doing, is that at its heart, with a categorical variable, you can never solve the problem, if you will, that at root, you're starting with just a bunch of binary variables. That's all there is to it. So even things like embeddings in neural nets, for instance, yes, what you're doing with the embedding is you are taking a look at some of the coefficients that are generated, or the weights, as they call it in neural network literature. However, at the very beginning, the input into that neural net is going to be a bunch of binary variables. And then it's just a question of what do you do with them. So, to that end, let's start looking at the data and let's start preparing ourselves for these exercises. And again, we'll explain how we will do the grouping exercise subsequently, but just know that that's what we're going toward. So we are going to be first, we're going to solve the problem of how do we group our variables, and then we are going to actually build our Mars models. So let's take a look at the code here. And so what we're going to do, and again, all of this code is available in GitHub. And so everything you see here is absolutely available to you for free. You just obey the license, as it were. And so what's the point of this first piece here? Well, the point of this first piece is simply to read in all of the different functions that I've written that are going to be useful for basic data analysis. And so, as I've said previously, the data set about which we will concern ourselves here, this is a data set that has to do with, and the description is in GitHub and further on Kaggle, this is the classic housing price data set available on Kaggle. So this is Ames, Iowa, years 2006 through 2010. And this is roughly what it looks like here. So you've got, there's the ID, there's the frontage, the lot area, the street, the alley, all sorts of stuff. Here's when it was built. Here's if there was a remodel, basement quality, all sorts of stuff in here, right? There's 81 different variables. Of course, one of them is the target variable, and the other is the ID variable. So there's really just 79. So you got 79 variables, not a lot of observations in the data. But this is the nature of the data set. And so what do you do with a data set? Is there some sort of canonical way to handle all this stuff? And the answer is yes, and that is the partition of variables into two kinds, continuous and categorical. So for instance, I would view year built, being numerical in nature, as a continuous variable, although it takes integer values, so it technically is not connected in its topological sense, versus something like roof style, which is clearly a categorical variable. So how do you deal with all this stuff? Well, we already know how to deal with it because we remember the probability integral transform. And so we're going to hit every numeric variable, every continuous variable with the probability integral transform. So we're going to transform year built. We are going to transform total basement square footage. We are going to transform garage year built. We're going to transform all of these things into their empirical cumulative distribution functions through the probability integral transform, which we discussed 2 videos ago. But wait, what if there's missing values? But we already know how to handle that problem too, right? So for categorical variables such as fence, all these NAs, because it's a categorical variable, we're simply going to treat them as just another category, the category of missing. And for the numeric variables, we're going to create missing indicators for those, as we discussed in the last video. And so we are going to then standardize all of this stuff, but prior to even doing that work, we first have to go through variable by variable and get a sense of what's going on. And that is the point of the data profiling function. So just to keep going down here, we'll set the target variable. So of course, in any data scientific exercise, you need to have a clue about what it is you're trying to model. The computer can't figure that out for you, so we will tell it what it is that we want to do. And then we are going to make sure that's always populated, because otherwise we're just wasting our time. And yes, it is good for us. All right. And so we were going to see, we're going to check and see if the offset is null, which in this case it is. So this part of the code just goes through and checks that. And again, the point of all this is that we are simply trying to automate as much as possible the data scientific work. We want to save our brain power for the things which actually require it, right? And so the point of some of that stuff then is the data profiling function. And so the idea with the data profiling function is to perform those basic checks on any data set you give it, to make sure that things are what you think they are. So one of the things it does is it goes through and checks for duplicate records. Are there duplicate records in the data? In this case, there aren't any, so that's nice. It also goes through the data profiling function. It checks through all the different columns and tries to guess at what would be an appropriate key for the data. And so in this case, it guessed that the key was the ID field. All right, so that's good. And again, some of this stuff, when you're working with subject matter experts on their data sets, they'll tell you this stuff, but it's always good to run checks on what they tell you just to make sure that everything is what people think it is. There is a difference between what is conceptually thought to be true and what is actually true empirically. Okay. And so now something else that this program does is it runs through all of the variables and it just samples some of the variables. And so you'll see that the univariate summary size is 10 and that the numeric threshold is 99. So what does that mean? Well, I'll show you. If you look at the output of the data profiling, what it is a list object. So in R, a list object is sort of your most basic object. You can think of it as a set. So it can contain all sorts of things. It can contain matrices, vectors, characters, all sorts of things. So that 10 in the univariate summary size, what that indicates is it's just going to pick the 10 most common values of the variable and show them to you. And the point of that is then you can kind of go through variable by variable and say, I think this is continuous, I think this is categorical. But you don't have to if you don't totally want to, because the program is going to go through and take a guess. How's it going to do it? Well, it's going to see how many of the values of the variable are in fact numeric. And if the percentage of values that are numeric, populated values, of course, exceeds 99%, then it's just going to go, it's continuous, or it's probably categorical. And then at the end, it's going to guess the metadata. And so it's going to produce something like this, and it's going to go, I think ID is continuous, because again, the computer doesn't know that it's just a key, it's a meaningless field, so we're not going to use it. I think zoning is categorical, and it's just going to go through and guess for each of them. And so that way, you don't have to do it fully on your own from the beginning. The program's going to go through and do it for you. Now, as we stated, though, in the metadata, and speaking of metadata, I should probably make this point as well. The hardest part about data science, and indeed most of life, is the bookkeeping. And so what you're doing with so much data science is you are taking your raw variables, you're transforming them in useful ways, such as the probability integral transform. Later on with Mars models, we will be transforming those into yet different variables. And that's all well and good, but then what you have to do is you have to unravel all of that to get back to your original data set, because that is the thing in which the client is interested. The client is not interested in all sorts of crazy transformations you do because you're worried about precision. The client is interested in making decisions, and that means translating all of the work you do back. And so a recurring theme then throughout these is that we will be creating these translation tables and metadata as we go throughout, so that once we get our model, we can then unravel it and put it back in terms of the original variables. And so if you look at the metadata here, you can already see that there's some stuff in here that we don't need. We don't want to consider the variable ID. We don't care about that variable for our analytic purposes. We don't care about the offset variable we created, which was just a placeholder. We don't care so much about that one either. And so then that is the point of this piece of code here, which is we're just going to get rid of the target variable. That shouldn't be in there. If you model a variable with itself, it's a really good model, and also it's very accurate and totally useless. So we're going to get rid of those guys. And that is the point of this code right here. There's the key. And let me get rid of that. And now, if you look at the metadata, what you'll see is that there is no longer ID is listed in the variables in consideration. All right. And so now we're just going to print the variables that we think are continuous, as well as some sample values from them. And then what you can do is you can go through and you can say, oh yeah, I think, yeah, that's definitely a continuous variable, or no, I don't think that's continuous. So for instance, right here at the top, MS subclass right here, that is a variable whose data type is numeric, but whose conceptual type is in fact categorical. And so that's why it's useful to go through and check just to make sure that, yeah, the ones that we think are continuous really are continuous. And so therefore we need to update, once you go and look through those, overall quality, overall condition, and once sold, all of these things are numeric data types, but conceptually categorical. So we'll just go through and fix those in the metadata. And then now if we look at the metadata, you can see that, oh, now MS subclass is in fact termed categorical. We're going to add a few new variables as well because this has to do with housing prices. We're going to look at the age, and we are going to update. We're basically just going to append those variables at the end. So you can see there they are down there. A couple of age variables. Okay. So we'll append those, and now the non-missing special values. So back to the topic of missing values, one of the things that sometimes also happens is that sometimes variables which are conceptually continuous, sometimes missing, they might also sometimes have like control values in them or some sort of special value that is not related to the rest of the values. And so you want to account for those and create indicators for those as well. But in this case, we have no such variables, and so we will not worry about them. And so now that we've used data profiling to get a sense of the metadata, we know what variables are in, we know the variables about which we care, we have declared which are categorical and which are continuous, so that's all. We have declared the phenomenon in question. This is all stuff that a human has to do, the computer can't guess. Now we will standardize the variables. So that's data standardization, all right? And again, topic of metadata, we produce a translation table. What does this look like? Well, it gives a one-to-one correspondence between the original variable and the output from data standardization. So lot frontage in the raw data has become two variables in the standardized data. One is just called variable one, and the second is variable one missing. So that's the missing indicator about which we spoke last time. And so you need that missing indicator for any continuous variables. Categorical variables like fence just become variable 78. And the other thing is that now if you look at this data here, what do you see? Well, now you see it's all straight numeric. So, you've got all these values between 0 and 1. That's our probability integral transform that we spoke of 2 videos ago. We've got our missing indicators. But now what's happened with all of these guys? So we saw that fence was, I think, variable 78, a bunch of zeros here, a bunch of integer values here. What we've done is we've taken every categorical variable and we've simply relabeled it. And the point of this is just to deal with the fact that categorical variables could take all sorts of values, but we don't really care what those values are for modeling purpose. We just need to know that they take them. So we relabel all of the categorical variables. If a categorical variable has 50 values, we label them 1 through 50. If it has 10, we label them 1 through 10. And that's what you're seeing here. And so that way we don't have to worry about, well, it's a categorical variable, but is it a character? Is it numeric? Who cares? It's 1 through n. That's what it is. And so that's the other thing that we do. And so then the translation table helps us translate, again, bookkeeping, it helps us translate back and forth between the raw data and the transformed data that will be the foundation of our modeling. Okay, so now we do one of our checks. So again, the way to think about this is as follows, which is that what does it mean to know something? What it means to know something is if you act on that knowledge, you obtain that which you expect, then you know something. So it's a very pragmatic William James sense of the word, pragmatism. So in this case, what are we doing? We're checking the coherence of the dimensions. So the number of columns in the standardized data, what do we expect? Well, for each categorical variable, we expect an identical column in the standardized data with just the values here replaced with 1 through n. But for every continuous variable, we expect 2 new columns in the standardized data, one which is the probability integral transform, the other which is the missing indicator. And so what should happen then is that when we take the metadata here and we double the number of rows which pertain to continuous variables and add to it the number of rows which pertain to categorical variables, that should all balance. And so these sorts of balancing will take place all throughout this code to make sure that we haven't accidentally added records to our data or lost them, or, oh, I wasn't expecting that column, and that sort of thing. It's the data due diligence aspect of data science, which is easily 80% of the job. We'll check and see if there's a weight variable, but we know there isn't, so we'll just include a dummy variable. And we will also include the key variable or variables, but in this case, just variable in the data. And so again, we check our dimensions before and after that. We will include the target and offset variables in the standardized data. So now in the standardized data, it is a perfect translation of our raw data. We've got all of our variables transformed. We've got our offset, we've got our weight, we've got our target. So now what? Well, among other things, we're going to update our translation table with our conceptual type. And then what we're going to do is we are going to declare all conceptually categorical variables as internally categorical. So in the R language, if you know you could have a categorical variable in R, that's called a factor. And what you can say is, you can say to R, oh, by the way, that's a factor. That is a categorical variable, and that's the point of the as factor function. Why does that matter? Well, because what we're going to do now is, and this, like I said, this goes back to what to do with categorical variables. How do you group them in some reasonable fashion? And the answer is, remember, every categorical variable with n values is really n binary variables. And so then what we're going to do is we are going to take that single variable and break it out into its n binary variables and do nothing with the missing indicators and the continuous variables because they're already numeric. So we don't have to worry about that. And so this is what's known as the design matrix. So you have your raw data, you have your standardized data, and then you have your design matrix that is going to come from the standardized data. And that's really going to be the place where you're going to be doing all of your modeling work, because then everything's populated, everything has been split out into its binary indicator variables, and everything has had the probability integral transform applied to it. And so we create our design matrix. First, we create our design matrix formula. We create our design matrix like that. And the formula looks exactly how you think. It's just, hey, here's what I want you to put in your design matrix. Now, the thing is that the design matrix, you have to do a little bit of work to put the additional columns in there. So obviously, if you have for a categorical variable, one of the values are taken, which means all of those binary columns sum to one, and therefore are linearly dependent. So you don't need all of them when you're simply considering linear models. However, we do want them, and so that is the point of create translation table, is we will put in those additional columns corresponding to what is sometimes known as the base level or something like that. And we will also create a a, uh, uh, a translation table, uh, for the design matrix. So let's add those columns there. Everything balances, yay us. And now we've got a second translation table. So what does this look like? Looks like this. So now what we have is we have our raw data. We've got a translation table between that and our standardized data. From our standardized data to the design matrix, we have a translation table between there. And so we know, for instance, that column 384 corresponds to the eighth value of variable 7. What's variable 7? I don't know. You go look it up in the original translation table in metadata. And that's it. That's the first piece of the modeling exercise here, which is to just look at the data. That's the point of data profiling. You look at the data, you determine what's continuous and categorical, you declare it as such, you then standardize the data with that information. You take that standardization and you create a design matrix out of that, and that's what's going to be used in the modeling efforts going forward, and in particular will help us solve the problem of what to do with grouping categorical variables. So what do we do with this information now? Well, among other things, we are going to use something like XGBoost on it. So what's XGBoost? XGBoost is simply it is one of multiple machine learning techniques I will not discuss it. There are many such discussions online, and so we don't have to worry about it here. The main thing we are simply going to do is use it. And so we're not going to walk through all of this data, but I just want to give you a flavor, or say all of this code. I simply want to give you a flavor of what's going on here. So we're going to read in the standardized data as well as the design matrix that we just created. And now we have this metadata file that we've written to the disk, and we can read that in, and it will tell us everything about our analysis here. So now our paperwork is paying off, say. So now we know all those things. We'll create a training testing split. We'll create design matrices used for XGBoost. Here are some general parameters for XGBoost. And I gotta say, XGBoost was very well programmed, and one of the nicest things about it, from our standpoint, is that you can, right here, end thread. So it is multi-threaded, which is very useful. So run that guy, and this just gives you a sense of the kind of results you can expect. You can predict, you can run the predict function, you can recover the error. So you see that this value here corresponds to that value there. Similarly, this value here corresponds to that value there. So that means that we understand, yep, okay, we get what's going on here. We do understand the nature of the model. Because it's XGBoost, it involves a lot of trees. You can actually dump the model and get a sense of what's going on. So for instance, there's the model dump, lots of pieces to it. So we will explicitly create some of those guys there, like that. And so what do you see here? Well, if we just simply look at our indicator functions here, what do we see? We see that this 0.934 whatever, that corresponds to this piece of the tree there. This 0.52 corresponds to this piece of the tree there. And finally, this 0.5 corresponds to this piece of the tree there. And that these counts here match these counts in here. So this is simply a demonstration that, yep, we get XGBoost, we can reproduce its results, we can reproduce its errors. We got a sense of what's going on. All right, let's get rid of those indicator functions. You also get a count of how many components are in the model. Apparently there are 350 there. We can figure out the round at which the testing data had the lowest error, which apparently was 49. Okay, so why is that important? Well, because what we're going to do next is, and again, all of this code is on GitHub. I created my own cross-validation function for XGBoost. And what that's going to do is, for a fixed set of parameters, so we got these parameters up here, it's going to go through and use those and then just cross-validate. And so what we're going to do is we are going to use cross-validation to get a sense of what parameters are best. So the rest of this file is hyperparameter tuning. We have a certain set of hyperparameters. We do cross-validation. We get errors. We go, okay, error goes up when I do this. It goes down when I do that. Okay, I'll use this hyperparameter. And that's all this file is. It's not an interesting file. It's just hyperparameter optimization for XGBoost. And then once you decide on a set of hyperparameters, you just apply the model and you output it. And the same thing holds true for the random forest modeling. It's the exact same kind of code, except instead of using R's XGBoost function, it uses R's random forest function, which is called Ranger. Again, Ranger is it's parallelized, so that's nice. And again, it runs nice and fast. And so what you want to do in both of these cases is you want to run it once and get a sense of how long that takes. And then that will give you a sense of how long cross-validation is going to take. And then you can run as many as for which you have time. So I'm not going to talk too much about random forest or XGBoost modeling because there's no reason to. There's all sorts of videos and books and articles on that kind of modeling, and the code is just running the function. So there's nothing interesting about that. It's just hyperparameter optimization. But the point then is that at the end of both of these, what you will then have is a machine learning model on your data, one XGBoost and one random forest. And so what that is going to do for us, among other things, is it's going to be a model which is, somewhat precise. So it's going to be precise, but it's not going to be explicable. We're not going to be able to say what the heck is going on inside there. Uh, but it will nonetheless be useful because it will, for one, serve as sort of an error bound of the kind of performance we can expect from our model, and sort of benchmark. But it will also be used when we group our categorical variables together. And that will be the topic of the next video, how you actually go about doing that and how you can then group your categorical variables and answer the question of how much weight is enough. I hope you found this video useful. If you have any questions, please leave them in the comments.